Okay, so let's get started with our review. Okay, perfect. So let's get started with our review of the exam 2 practice exam for Chem 101. So we're provided a periodic table, but let's just start delving into the questions here. So in the first question, we're asked, what mass of ammonium oxalate contains the same mass of nitrogen as 24.5 grams of calcium nitrate? So our first order of business in this problem is to write out the formula. So for ammonium oxalate, we have ammonium, which is NH4+, and oxalate, which is C2O4 2-. If we cross our charges, that gives us NH4 C2O4. So that's ammonium oxalate. Calcium nitrate. So we have calcium, and what's the typical charge of calcium? Yep, 2+. And nitrate, what's the formula of nitrate? NO3, and what's the charge? Minus. So we cross our charges, and that gives us CaNO3 2. Okay, so we're going from grams of calcium nitrate. We're going from grams of calcium nitrate, and our end goal after this unit conversion is to report the grams of ammonium oxalate. Now, our central relationship is the mass of nitrogen. And if they have the same mass of nitrogen, you can also say that they have the same moles of nitrogen, right? Because a mass ratio and a mole ratio for the same element are equivalent, right? Okay, so we're going to go from grams of calcium nitrate, and our center point, our center connector, is going to be moles of nitrogen. Now, from mole, how are we going to get to moles of nitrogen from grams of calcium nitrate? What intermediate units are we going to go through? Moles of what? Exactly. So we're going to go through moles of calcium nitrate to moles of nitrogen, and then to moles of ammonium oxalate, sorry. Okay, perfect. Now that we have our problem-solving manifold prepared, all we have to do is execute on it. So we have 24.5 grams. We have 24.5 grams of calcium nitrate. And really quickly, did someone have the molar mass of calcium nitrate? Does someone have the molar mass of calcium nitrate? 164. So in 1 mole of calcium nitrate, we have 164.1 grams. Perfect. Now, my question to all of you is, how many moles of nitrogen do we have per mole of calcium nitrate? How many moles of nitrogen do we see? 2. Okay, perfect. So we're now at this stage. And now my question to all of you, in 1 mole of ammonium oxalate, we have how many moles of nitrogen? How many moles of nitrogen do we have per mole of ammonium oxalate? 2. And then finally, how many grams do we have in 1 mole of ammonium oxalate? 124.12. Perfect. Would I be able to borrow someone's calculator for this, just to double check? We now have our raw numerical form. Now all we have to do is punch this into the calculator and report our final answer. So we have 24.5 divided by 164.1 times 2 divided by 2 times 124.12. And that gives us a final mass of 18.5 grams of ammonium oxalate. I'm just going to check the molar masses really quickly. Okay, the first molar mass looks good. And the second molar mass looks good. So in the end, we're able to report the mass of ammonium oxalate with the same mass of nitrogen, which in other words means the same moles of nitrogen atom. Does that make sense? Does everyone get how we set up our unit conversion manifold? How we're going from grams of calcium nitrate to grams of ammonium oxalate, and we're going through the moles of nitrogen. Because we're given in the problem, we're looking for two samples with the same moles of nitrogen. Does that make sense? Okay. Any questions on this example? Let's keep going then. So in this next problem, it's asking how many grams of nitrogen are in this many number of molecules of nitroglycerin. Okay, so we're going to go from molecules. We're going to go from molecules of nitroglycerin. And if we want to report grams of nitrogen, in the end we want to report grams of nitrogen, how are we going to get grams of nitrogen? We get the mass of nitrogen from what? Where do we calculate mass from? Periodic table and what other quantity? A molar mass and moles, exactly. So we're going to need the moles of nitrogen. And where are we going to get the moles of nitrogen from? Where do we get the moles of an element from? Yeah, moles of a compound. Yeah, exactly. So we're going to need the moles of nitroglycerin, which is C3H5O9N3. Okay, perfect. So we have our problem-solving manifold set up. So now all we have to do is execute on that manifold. So we have 4.369 times 10 to the 17th molecules of C3H5O9N3. Okay. Now, to go from molecules to moles, what units are going to be on top? Moles. So in 1 mole of C3H5O9N3, we have how many molecules? How many molecules are in a mole? What was that? Yep, Avogadro's number, which is 6.02 times 10 to the 23rd molecules per mole. So it allows you to go from moles to particles. Okay, now my question to all of you is how many moles of nitrogen do we have in 1 mole of C3H5O9N3? How many nitrogen atoms do we see? 3. Okay, perfect. And I apologize that the font size is getting small, but these one-line conversion strings have a lot of steps. My final question is how many grams of nitrogen do we have per mole of nitrogen? 14. Yeah. Now all we have to do is punch this into our calculator. Does this setup make sense to everyone? Does the logic behind it make sense? Okay. We're going 4.369 EE17 divided by parentheses 6.02 EE23rd. Remember, Avogadro's number needs to be entered in parentheses in your calculator or you'll get the wrong answer. So times 3 times 14, and that in turn gives us 0.000030481 grams of nitrogen that we can convert into 3.048 times 10 to the negative 5th grams of nitrogen. And your calculator will just do that if you input the decimal to scientific notation function. Yes.
You said in the calculator to put parentheses around this?
Yes, yes. Mm-hmm. Because otherwise, the calculator will think, I'm dividing by 6 and then I'm multiplying by 10 to the 23rd.
Oh, okay.
Yeah.
Okay.
Yeah.
Just put 6.
That should work, but I always like to put in parentheses just to be 100% sure and to avoid any potential calculator errors. Any questions on this example, or can we move on to the next one? Don't be shy to ask questions. I know how to do all of these front to back, but if you have any questions, this really is your time to ask. Can I move on? Okay, so let's move on to the next one. And in this case, a lot of these questions are almost direct pulls from the homework. So I'm asking what volume, what is the volume of a sample of pyridine that contains 14.5 grams of carbon? So we're going from grams of carbon, and in the end, we want to report the milliliters of pyridine. Now, how do I report volume? If I'm given the density, where am I going to get the volume of pyridine from? Yes, exactly. So density allows us to convert between mass and volume. So we're going to consider the grams of pyridine. Okay, and now where are we going to get the grams of pyridine, which is C5H5N? Where do we get the mass of something from? Moles, exactly. So we're going to need the moles of pyridine, which is C5H5N. And where do we get the moles of pyridine from? If we're starting from the grams of carbon, what's our stepping stone? Yeah, exactly. Okay, perfect. So now we're ready to execute on this. Now we're ready to execute. So starting off with 14.5 grams of carbon. In 1 mole of carbon, we have how many grams? 12, yep. Okay, if we're going from moles of carbon to moles of pyridine, what units need to be on top? Moles of pyridine, exactly. And in 1 mole of pyridine, C5H5N, we have how many moles of carbon? 5, exactly. You see 5 moles of carbon because it's C5H5N. Finally, how many grams are present in 1 mole of pyridine, in 1 mole of C5H5N? Would someone from the class like to provide me with the molar mass? 79, if I'm not mistaken. 12 times 5 plus 5 plus 14 is 79. Yep. So we have 79 grams per 1 mole of pyridine. The 78 versus 79 wouldn't actually affect the magnitude of your answer substantially, but you always just want to make sure that the molar mass reported is exact as possible when I check your work. And then finally, if we're going from grams of pyridine to milliliters of pyridine, what needs to go on top? Milliliters. And in 1 milliliter, we have how many grams of pyridine? Looking at our density, how many grams do we have? Yep, 0.982 grams. Okay, all we have to do now is punch this into our calculator. 14.5 divided by 12 divided by 5 times 79 divided by 0.982. And that gives us a mass of a volume of 19.4 milliliters of pyridine, which on an order of magnitude sense seems reasonable. This compound is mostly carbon. Does that make sense to everyone? Any questions on this example? Does this remind you of some of the homework? Yeah, so I'm not just giving you out of the blue questions, and I'm not just assigning you homework as busy work. It's designed to prepare you for the exams and prepare you for the questions that you'll typically be asked. Is it okay if I move on? Is everyone comfortable so far? Really, don't be shy to stop me. It's to your benefit if there's anything you want me to explain in detail. This one's fun. Unfortunately, we'd actually do a lab almost exactly like this procedure. You did the calculations for the limiting reactant lab, right? This overall problem is very, very similar. And if you didn't see it, the parallels to the laboratory, it's also found as a homework problem on Canvas as well. So this is a type of problem that you should expect to be able to handle. So a student is given a carbonate of this form. Okay, we know X is an unknown metal cation. So we take 2 grams of our unknown carbonate and we heat it to yield 1.67 grams of the metal oxide. Okay, so we're asked a series of questions that are designed to help us reach the answer. So in general, looking at oxygen, what is the preferred charge of oxygen in a metal oxide? Yeah, 2 minus, right? It's a 6A element. 6 minus 8 gives us -2. Okay, looking at our metal, if we have X2CO3, what is the potential charge of X? So let's think about this really carefully. If we reverse cross our charges and we want to figure out our charges from the formula, we'd end up with a predicted charge of X of +1 and a predicted charge of carbonate of 2-. Does that make sense with our literature charge for carbonate? Yeah, so then the charge for X is going to be +1. Likewise, in X2O, if we reverse cross our charges, we get X plus and O2-. So what's the charge of X? +1, exactly. Okay, so X2CO3 is going to decompose upon heating. So if we have X2CO3 and we heat it, we're going to get out X2O. And then this is something that we'll touch on and that we've actually seen before in laboratory. When you heat a carbonate, you get out a metal oxide. And what's the other byproduct? Yep, carbon dioxide. Exactly right. You can also figure this out by conservation of atoms. So we see that the difference between X2O and X2CO3 is 1 molecule of carbon dioxide. So these are literature reactions. On the actual exam, I'll tell you the product to make it a little bit easier on you. You don't actually need the chemical equation to solve this problem. I had this as a writer question to make sure people knew how to write decomposition equations. On the actual exam, you won't have to write an equation from scratch this time. Does that make sense to everyone? Okay. So next we're asked to calculate the mass loss during heating. So if we start off with X2CO3, if we start off with 2.0 grams of X2CO3, and in the end, after heating, reading through the problem, we get 1.67 grams of our metal oxide. Okay, what is the remaining mass going to be? By conservation of mass, can we calculate the mass of carbon dioxide that we've lost from our solid? Can we? Yep, exactly. We can calculate it via difference. And 2.0 minus 1.67 gives us 0.33 grams. Does that make sense to everyone? This is just conservation of mass. The mass before and after a reaction is constant. Does that make sense so far? Have we seen these components in previous problems? Have we seen this idea of conservation of mass before? Okay. Any questions before we move on to the next logical step in this process? Yes.
So the decomposition, you said that what yields carbon dioxide?
Yeah, when you heat a metal carbonate, which is this CO3, they'll decompose to yield a metal oxide and carbon dioxide. I wouldn't stress too much about it for now. I'll give you the equation for this exam because we haven't yet covered fully the rules for predicting chemical reactions. The reason why I want you to have the equation is if you wanted to use the equation for example, the stoichiometry approach, you can. You don't actually need the stoichiometry approach for this problem. Does that make sense? Perfect. So, what is the identity of the mass loss during heating? So this is carbon dioxide, and we know we have 0.33 grams of carbon dioxide. Can we calculate the moles of compound loss during heating? Can we calculate the moles of carbon dioxide? Can we calculate the moles of carbon dioxide given the mass? Yes. So we know in 1 mole of carbon dioxide, we have 44 grams. So we have 0.33 divided by 44, and that in turn gives us 0.0075 moles of carbon dioxide. Okay, perfect. Now this is the key to solving this problem. It may look very innocuous, but this is the key to solving this problem. And to showcase this, let's take a look at our chemical equation. Let's take a look at our chemical equation once again. So, where is all of our carbon coming from? Where is all of our carbon coming from in CO2? Where did all the carbon in carbon dioxide come from? Carbonate, exactly. So then we know that the moles of CO2 are going to be equal to the moles of carbonate, right? Because all the carbon atoms in carbon dioxide came from our carbonate, right? So without even looking at the chemical equation, we can establish a mole ratio. You can also use stoichiometry if that's what you prefer. But the reason why I like showcasing this idea of atom conservation is it allows you to establish mole ratios, even if you don't necessarily have a full balanced equation. Does that make sense? Does everyone understand why the moles of CO2 equal the moles of carbonate? Because we have the only carbon source and the only product containing carbon. And that's as a hallmark of these sorts of conservation problems. So then, given that we have 0.0075 moles of carbon dioxide, my question to all of you is how many moles of carbonate do we have per mole of CO2? What's our mole to mole ratio? You can use the equation if you want, or you can use the conservation approach. What's our mole to mole ratio? 1 to 1, exactly right. All the carbon from carbonate ended up in carbon dioxide. Now, given that we're asked to report the mass of carbonate, we need to convert from moles of carbonate to grams. So how many grams are in 1 mole of carbonate? How many grams are in 1 mole of carbonate? What's the molar mass of carbonate? So 12 plus 16 times 3, it's a mass of about 60. So now we can punch this into our calculator. 60 times 0.0075, 60 times 0.0075, and that gives us 0.45 grams of carbonate. Now it may just seem like we've gone quite a circuitous route, but we are starting to be able to figure out the identity of our metal X. Okay? Does this logic make sense? Does this line of logic make sense? We measured the mass loss. The mass loss is carbon dioxide. All of the carbon atoms in carbon dioxide came from carbonate. So then, from the moles of carbon dioxide, we can calculate the grams of carbonate. Does that make sense? We're just doing mole-to-mole conversions and mole-to-mass conversions. Now, we're asked to determine the mass of X in our sample and in our unknown carbonate. Sorry, this is a typo. So, given that we have 2.0 grams of our carbonate, if we make a pie chart, some portion of our mass, in this case 0.45 grams, is our actual carbonate. What is the remaining mass of our sample? If we have 2 components, a metal X and carbonate, what's our remaining mass going to be? If we have 0.45 grams of carbonate, what is this other mass representing? What is it the mass of? The metal, exactly. So this other mass, the other portion of our 2 grams, is our metal X. Okay, so then our grams of X are equal to 2.0 minus 0.45 grams, and for our grams of X, we get 1.55 grams. Everyone following so far? Okay. Now, just as a refresher, for X2CO3, we have 1.55 grams of X and we have 0.45 grams of carbonate. We also know we have 0.0075 moles of carbonate. Now, from this information, we're going to do a mass to mole conversion. So if we need to calculate the molar mass of X, we need the grams of X per mole of X. This is our goal, right? So then, do we have enough information, given that we know the moles of carbonate? Can we figure out, we have the grams of X right here, so we have that checked off. Can we figure out the moles of carbonate? given the formula? Can we figure out the moles of carbonate given the formula? Yes. All we have to do is take 0.0075 moles of carbonate. And my question to all of you is, how many moles of X are present per mole of carbonate? What is our mole to mole ratio? If it's X2CO3, how many moles of X do we have? 2. Because we have 2 moles of X per 1 mole of carbonate. Okay, so then that in turn gives us 0.015 moles of X plus. We now have all the information we need to calculate the molar mass. So we take 1.55 grams of X over 0.015 moles of X. So 1.55 divided by 0.015 gives us a molar mass of 103.3 grams per mole of X. Now let's take a look at our periodic table now. Let's zoom in on our periodic table and let's try and find what element in the periodic table has a mass close to 103. Let's go all the way up to our periodic table and let's do some searching. So what element in our periodic table has a mass close to 103? What was that? Rhodium, yep, that would be a reasonable response. Are there any others in the range of 100 to 109, anything in this general range? Our measurement's not super precise, but rhodium seems reasonable to me. Other reasonable answers, you could guess palladium, ruthenium, even silver. All of those are acceptable. I just want to see that you're actually referencing the periodic table to pull up your molar mass. When I designed this problem, it was silver, but our mass calculations weren't precise enough to really tease that out. So you can write this as silver carbonate or rhodium carbonate or palladium carbonate. All of these are acceptable answers because they're within the margin of error. I mean, if you don't get an exact spot-on match for a molar mass, just look for the closest thing or check your calculations. We know our calculations are pretty good, so we have a pretty wide range to guess. You just want to make sure you're guessing things that are reasonable. So make sure, why could I reasonably say silver, rhodium, and palladium? Could all of these species adopt a +1 charge? Could all of these species actually adopt a +1 charge? Are all of these transition metals or transition metals that have a trend for a +1 charge to be favored? Yes. So just make sure that your guesses make chemical sense. And we have the rules for that. Does that make sense? So when we break down this problem, is there any part that we haven't really done before in some form? Have we done conservation of mass calculations? Have we done this kind of molar mass calculation at the beginning of chapter 4? Yeah. So all the pieces are there. This is just a different arrangement of those pieces. And I would look at the homework assignments on Canvas for additional practice because I have at least 2 of these in the homework. Okay. Let's now move on to some more benign mass mole conversions. We're asked how many moles of hydrogen are in a 15-gram sample that is 62% carbon by mass that contains 6 hydrogen atoms for every 3 carbon atoms. Wonderful. Now, as we discussed in class, an atom ratio is the same as a ratio of what? Moles. So we essentially know in this problem we have 6 moles of hydrogen per 3 moles of carbon. We know that just given from our atom ratio. So let's set up a problem-solving scheme to get us from start to finish for this problem. So we're given the grams of sample, okay? We're given the grams of sample. And in the end, we want to be able to report the moles of hydrogen. So what's our intermediate stepping stone? Where are we going to get the moles of hydrogen from? Given that we know the moles of hydrogen per mole of carbon. Where are we going to get the moles of hydrogen from? Moles of carbon, exactly. Okay, and where are we going to get the moles of carbon from? grams of carbon. And can we get the grams of carbon from the grams of sample given our mass percent? Yes. So given that we have 15.0 grams of sample, we know this 62%. How many grams of carbon do we have per how many grams of sample? 62 over 100. Yep. This is the way to write out mass percent as a conversion factor. Then in 1 mole of carbon, we have how many grams of carbon? 12. And then finally, how many moles of hydrogen do we have per how many moles of carbon? What's our mole to mole ratio? 6 to 3. So all we have to do is now execute on that. So we have 15 times 62 over 100 divided by 12 times 6 over 3. And that in turn gives us 1.55 moles of hydrogen. Does that make sense? So you have all the pieces. What's important and what I highly recommend that you do is you make these solution maps. The reason why I use them is they help you organize your thoughts and they can help you tease out the solution even though you may not necessarily know each of the individual steps. Just by looking at the units, you can go from start to finish. And that's the power of unit analysis, you know. I could not even necessarily know what any of these terms mean, but if I know that the units cancel, my response is at least reasonable. Okay, our next question, we're asked to calculate the mass percent and mole percent for each element in sulfuric acid. So what's the formula of sulfuric acid? Yep, H2SO4. So first, let's do the mole percent. So the mole percent, let's do hydrogen. So how many moles of hydrogen do we see? How many atoms of hydrogen do we see? 2. So we have 2 moles of hydrogen, and how many total moles? How many total atoms do you see? 7. Okay. So we have 2 over 7 times 100, and that in turn gives us 28.6%. Let's do the same thing for sulfur, the mole percentage of sulfur. We have 1 mole of sulfur over 7 moles times 100%. And that in turn gives us 14.3%. Finally, let's do the mole percentage of oxygen. We have how many moles of oxygen? How many moles of oxygen do we have? 4. And how many total moles? Yep. So times 100%. That in turn gives us 57.1%. As you can see, all of these percentages add up to 100. So that means we're doing something right. Does that logic for mole percentage make sense? Any questions on how we calculated the mole percent in this case? Does it make sense to everyone? Really, don't be shy to stop me. Don't be shy to ask questions. As you see, if we're explaining through and walking through, each of these questions don't take a very large amount of time. Yes?
So the 7's from like the sum of all.
Yes, yes, yes. Because 1 plus 2 plus 4 is equal to 7. Good question. Thank you. So now let's move on and let's calculate the mass percent and our overall mass. So first, let's figure out the molecular weight of sulfuric acid. So we have 1 gram per mole. We have 2 hydrogens plus 32 gram per mole, and we have 1 sulfur, and 16 gram per mole, and we have 4 oxygens. That in turn gives us a molar mass of 2 plus 32 plus 64, a molar mass of 98 gram per mole. So this is the total mass that we're going to use in our calculations for the mass percent. And really, I like calculating the molar mass in this way because it makes it very easy for me to calculate my mass percent. To showcase this, if I want to calculate the mass percentage of hydrogen, I take my 2 grams that I calculated up here. I have 2 grams of hydrogen, and I divide by my total mass. What's my total mass? 98, exactly. So there's a reason why I choose a particular way of calculating things, because it saves me time and allows me to utilize my calculations in multiple different ways. Okay, let's now continue on and let's calculate the mass percentage of sulfur. Did we already calculate the mass of sulfur? Yes. What is it? 32. So we 32 grams of sulfur over 98 grams times 100%. So 32 divided by 98 times 100 gives us 32.65%. And then finally, we can finish off with the mass percentage of oxygen. And what's the mass of oxygen? What's 16 times 4? Do we have that already? Yep, exactly. So we're just going to plug in our 64 grams over 98 grams times 100%. Let me clean up that 64 so it's a little easier to see. So we have 64 over 98 times 100, and that in turn gives us 65.31%. And as you notice, all of your percentages will add up to 100% if you've done this method correctly, right? If you've accounted for every single element in your compound, your mass percentages should add to 100. Does that make sense? Okay. So, any questions on this example? Have we done something similar in lecture? Yeah, almost this exact example. Okay, let's now approach an empirical formula problem. A Ascorbic acid or vitamin C is 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. So we're asked to calculate the empirical formula. So I'm gonna put some labels here. Carbon is N1, hydrogen is N2, oxygen's N3. It's perfectly arbitrary, but that's what I'm just going to choose, and that's what we're going to stick with for this problem. If you chose different N1, N2s, and N3s, that's more than okay. It really does not matter in the slightest. So I'm going to take the ratio, and I'm going to calculate my mole ratio, because fundamentally, what does the empirical formula represent? It's a ratio of moles, exactly. So let's take N2 over N1. So given N2 is hydrogen, we're going to plug in the mass percentage of element 2 over the molar mass of element 2 times the molar mass of element 1 divided by the mass percent of element 1. Okay, so what's the mass percentage of hydrogen? 4.58%. What is the molar mass of hydrogen? 1 gram per mole. What is the molar mass of element 1, which is carbon? 12. Okay, and what is the percentage of carbon? 40.92%. Okay, perfect. Grams per mole cancel. We're left with a unitless number. So N2 over N1, which is the moles of hydrogen per mole of carbon. 4.58 times 12 divided by 40.92. And that in turn gives us 1.34 moles of hydrogen per every 1 mole of carbon. We'll leave this one alone for now. Let's calculate our second mole ratio. So again, your mole ratio should always be respect to the same element. So if we have the mole ratio with respect to the moles of carbon, which is N1, we should keep that consistent. So then, the moles of oxygen per mole of carbon are going to be equal to the mass percentage of oxygen over the molar mass of oxygen times the molar mass of carbon over the mass percentage of carbon. Does that make sense? We're using the exact same equation, except we're plugging in the mass percent and molar mass of element 3 instead. Okay, so now from this information, we know that N3 over N1, if we punch this into our calculator, we get 54.50 over 16 times 12 divided by 40.92. That in turn gives us 0.998 moles of oxygen per mole of carbon. And our rule is if we're within 0.02, then you can round. Otherwise, you cannot. So then, we need to get a whole number out of this. So what do we need to multiply both of these decimals by to get a whole number? I see this 0.33. This 0.33 corresponds to what fraction? 1/3, right? So what do I need to multiply 1/3 by to get rid of that fraction? 3, exactly. So then, in the end, we have, for our moles of hydrogen, we have 1.34 times 3. For our moles of oxygen, we have 1 times 3. And for our moles of carbon, this 3, when we multiply by 3, what are we multiplying? 3 of what? 3 moles of what? 3 moles of carbon, exactly. So how many moles of carbon do we have? 3. So then, combining this together, we have C3H, so this turns into 4O3. There we go. So that's our empirical formula. Does that logic make sense to everyone? Does it make sense where we got all of these numbers from? Okay. Now we're given in this next part that the molar mass of vitamin C is 176 gram per mole. So looking at C3H4O3, the first thing we need to do is we need to calculate the molar mass of this empirical unit. And we can do that really quickly. So we're taking 12 grams times 3 plus 1 gram times 4 plus 16 grams times 3. And that in turn gives us 88 gram per mole. Now, given that we know the molar mass, we can calculate the number of these empirical formula units by taking our molar mass of 176 gram per mole and dividing by our empirical mass of 88 gram per mole. And since we've done everything correctly up to this point, we get a nice whole number value of n. If your n is a fraction, something has gone seriously wrong. Does that make sense? Okay, so we get n equals 2. So we're going to take each of our coefficients and we're going to multiply them by 2. So that's going to lead us with C. What are our new coefficients? So we have C, 6, H, 8, O, 6. There we go. Vitamin C's formula calculated relatively quickly. Does that make sense to everyone? It's not too bad once you go through it, right? Okay. Any questions on this example? Wow, we've only been here for an hour and we're almost done with the exam. So we're on pace. Okay, so I'm just going to tell you off the bat, we're likely not going to be able to, next lecture, get to pH in detail. You don't have to worry about this question, but I'll show you how to calculate it. So pH is equal to 14 minus POH, which is equal to 14 minus negative log of the concentration of OH. For a strong base, the concentration of OH is equal to the concentration of NaOH. So our pH is equal to 14 minus negative log of 0.015. Okay, so 0.015 log negative minus 14, and that in turn gives us a pH of 12.2. We'll talk about this in more detail in chapter 7, which is the next chapter in the sequence. So don't worry about this for today, but for completeness sake, here's the solution on how you calculate pH given the concentration of strong base. Titration curves as well are going to be delayed, but we will have to use data from titration curves to complete titration stoichiometry. You will be responsible for a potential titration stoichiometry question. Just like that, the calculations that we performed in the titration labs. That's what you're going to be up to responsible for. Yes, it's almost exactly identical. The labs that we perform have almost the exact same calculations. So in a titration curve, the equivalence point, quite simply, The equivalence point is the region where your curve experiences the greatest inflection, which is this point right here. So at the equivalence point, we know that the moles of acid are equal to the moles of base times the stoichiometry coefficient, stoichiometric ratio. So it's not that the moles of acid and base are equal, it's that they're present in stoichiometric amounts, okay? Does that make sense? We have enough of acid and base to completely react, okay? It's not always at pH 7, but it's clearly visible in these curves, but it's the point with the greatest inflection, the point where the line is most vertical. We'll discuss this more in chapter 7. Okay. So our goal now is to estimate the volume of NaOH needed to neutralize 10 mils of lactic acid. So what volume? Reading down from this chart, about what volume do we have here? If this is 10.00 and we're about halfway between 9 and 10 mils, what volume was required? If it's between 9 and 10? Yep, so it's about 9.50 milliliters of NaOH. Does it make sense where we got that number from? We traced the volume at the equivalence point down, and that gave us the volume of NaOH needed to completely react with our lactic acid, or at least to reach this first equivalence point. Does that make sense? Okay. So on the exam, I'll probably replace this with like a picture of a burette. So you'll have to do some burette reading instead of reading this titration curve. So that way you're still reading a volume from not just given a number. You'll actually have to calculate the volume given a piece of data, but something similar to that. Okay. So we're next going to have to write an equation for the reaction of our acid with sodium hydroxide. Okay. So as we haven't completed the chapter on acid-base chemistry yet, this will mainly be the purview of next class session or later class sessions after the exam. Well, first and foremost, we write the formulas of each of our reactants. And in an acid-base reaction, our H plus reacts with OH minus, and the fastest way to predict the products is you swap your cation and your H plus source. So in turn, we end up with sodium propionate and water. So an acid-base reaction typically produces a salt and water. And in this case, what is our mole-to-mole ratio? What's our ratio of sodium hydroxide to propionic acid? Just looking at this equation, which we've balanced already. 1-to-1. So this is another 1-to-1 titration. You may not see a 1-to-1 titration on the exam necessarily if I decide to make a stoichiometry question. The stoichiometry may be 2-to-1, 3-to-1, 2-to-3. So key thing, this ratio is obtained from the chemical equation. This is the bedrock of stoichiometry. Okay, so now we're asked to calculate the concentration of the unknown propionic acid solution. So we're going to assume it required 10 milliliters to completely neutralize the propionic acid solution. Okay, perfect. We have enough information to proceed. So we know we have 10.00 milliliters of our acid solution. We also know, reading through our chemical equation, what is the molarity of our sodium hydroxide? What are we given for the molarity of our sodium hydroxide? Yep, 0.015. So we have 0.015 molar NaOH, and we know that it required 10.00 milliliters of NaOH. And reading the problem further, we know that we've titrated how many milliliters of acid? How many milliliters of the propionic acid did we titrate? 5. So let's plug that in. Okay. So then, given this data, we're going to first start from the volume of NaOH, and we're going to calculate the moles of NaOH. From the moles of NaOH, given that we know our chemical equation, can we calculate the moles of acid from our moles of NaOH? At the equivalence point, do we have a relationship between the moles of NaOH and the moles of acid? Yes, in this case, what's our relationship? What's our ratio? 1 to 1. So you can go from moles of NaOH to moles of acid. And then given the volume of acid, we can go from moles of acid to the molarity of acid. Does that make sense? Okay, so now that we have our problem-solving scheme in place, let's just execute on that scheme. So we have 10.00 milliliters of NaOH. We know that there are 10 to the negative third liters per 1 mil. And we know that we have 0.015 moles of NaOH in 1 liter. Now my question to all of you is, how many moles of acid do we have per mole of NaOH? What is our mole to mole ratio? 1 to 1, given from our chemical equation. And then finally, we're going to divide by our volume of 10 milliliters. And we know that in 1 milliliter, we have 10 to the negative third liter. So this conversion factor cancels, and we're left with 10 times 0.015 divided by 10. And that in turn gives us a final concentration, of acid of 0.015 moles of acid per every 1 liter, or 0.015 molar. Does that make sense to everyone? Do these calculations look almost exactly identical to the vinegar lab and to the standardization lab that we ran? Would you be comfortable doing these calculations inspired from the lab on an exam? Sure, definitely. But fundamentally, this is just stoichiometry. Mm-hmm. Yes?
So the ratio comes from this equation?
Yes, exactly. Yeah. And that's the key principle of stoichiometry. You use your chemical equation to get the mole to mole ratio of one reactant to another. Mm-hmm. So let's now take this one step further. And let's continue. Sorry, the touch screen is giving me a little bit of problems. Let me reopen it and we'll resume momentarily. Okay, don't worry about the buffer region and half equivalence point. If you're curious, we'll talk about this more in chapter 7. This is the buffer region. And the half equivalence point is halfway to the equivalence point. So if this is approximately 9.50, the half equivalence point will be about here at approximately 4.75 milliliters. Don't worry about that for now, but just for completeness on this problem. I want you to focus on the acid-base stoichiometry portion. This practice exam was designed assuming we got to chapter 7. We're slightly behind, but it's no worries. Now, this next question is something that you should be able to do. So a student attempts to titrate citric acid, which is a triprotic acid, with the same concentration as the propionic acid solution. What volume of NaOH would be required to reach the equivalence point? Okay, so we know for propionic acid, which is CH3, CH2, CO2H, it reacts with 1 molecule of NaOH, and in turn we make sodium propionate and water. Now, if we have a triprotic acid, which is H3C6H5O7. So we have 3 protons. So then, how many molecules of NaOH, how many hydroxide sources will we need to react with all of these 3 H pluses? How many NaOHs will we need? 3. Exactly. So in turn, we get Na3C6H5O7 plus 3 H2O. So triprotic, 3 protons requires 3 equivalents of monoprotic base. So then, looking at this mole ratio, if we compare the moles of NaOH, how many moles of NaOH do we need per mole of citric acid? What is our mole ratio? What is our mole ratio? Moles of NaOH to moles of citric acid. How many moles of NaOH do we need? How many NaOH molecules do we need? 3. So it's 3 to 1. So then, based on this idea, we need 3 moles of NaOH per 1 mole of citric acid. And given that we're starting with the exact same concentration, of citric acid as propionic acid. So we're starting with the exact same concentration. So if we have 0.015 moles of citric acid per 1 liter, we know the moles of NaOH required to react with the citric acid, and we know what is the molarity of our NaOH solution. What's the molarity of our NaOH solution? Well, let me rephrase. What volume of this citric acid solution are we titrating? If it's the same volume as our propionic acid, what volume of propionic acid did we titrate? What volume of propionic acid did we titrate all the way at the beginning of this question? 10 or 5? 5, okay. So we're gonna plug in our 5 mils. Okay, perfect. So far we have figured out and we have calculated the moles of NaOH required to react. To go from the moles of NaOH to the volume, what quantity do we use? Do we know in 1 liter how many moles of NaOH do we have in our solution? Do we know the molarity of our NaOH solution? Looking all the way up here, do we know the molarity of our NaOH solution? Yep, so we'll plug in our molarity. So in the end, the molarities are the same, so they cancel, and we end up with a volume of 15.00 milliliters times 10 to the negative 3rd liter per mil, which gives us 1.5 times 10 to the negative 2nd liter. Now, the math is not as important here as what you can derive from the chemical equation. What can you derive from this chemical equation? So looking at this chemical equation in detail. In our original problem, oh, there's one typo here. This should be 5. So then this should be 0.075 and 0.075 molar. So let's adjust that. So these molarities are not the same, so let's punch that into our calculator really quickly. And that would give us a volume of 0.0. of 7.5 milliliters. In other words, 7.5 times 10 to the negative third liters. Now, if we compare, it took us 7.5 times 10 to the negative third liters of sodium hydroxide with our triprotic acid. With our monoprotic acid, let me punch that in. Give me one moment just to check there are no calculator errors here. Yep, that looks fine. Yep, looks fine. Okay, so let's walk through this one more time. So we've calculated the concentration of our propionic acid, assuming a 1-to-1 ratio. So we know to titrate 5 mils of acid, it required a total of 10 milliliters of sodium hydroxide. Perfect. Now, in this problem, we know that based on our stoichiometry, it takes 3 moles of sodium hydroxide per every 1 mole of acid. If we know that the concentration of acid is the same, and we're titrating the same volume, because it takes 3 times the number of moles of sodium hydroxide to react with 1 mole of acid, we would expect it would take triple the volume of NaOH. So let's show that. So we have 0.0075 times 5 times 3 divided by 0.015. So in the end, we would expect, given the molarity of our sodium hydroxide solution, that it would take, let me take a look at this one more time just to see what's going on here. Ah, I see the problem. The volume of NaOH is correct as 10 mils, but the volume of acid is 5 mils. So it's the initial concentration where we made a calculation error. My apologies. So our concentration of the molarity of our propionic acid solution is 0.03 moles of acid per liter, or 0.03 molar. Okay, plugging that 0.03 molar for our propionic acid in for our concentration of citric acid gives us the following result. So 0.03 times 3 times 5 divided by 0.015. And that in turn gives us an expected volume of 30 mils, or 3.0 times 10 to the negative second liters. So then, it took us about 30 mils for our triprotic acid, while it took us 10 mils for our monoprotic acid. Now, what's the difference between these two volumes? 30 mils is how many times 10? 3. What is the difference in our mole ratio? Does it require 3 times the amount of NaOH for our triprotic acid? Yes, so then does it require 3 times the volume of NaOH for our triprotic acid? Yes. So the key thing is you don't necessarily have to go through and fully compute the exact volume. You can look at the relative stoichiometry in your 2 reactions and then simply multiply the volume of NaOH required by the new stoichiometric coefficients. So we have 3 times the amount of NaOH required, so it requires 3 times the volume of NaOH for this triprotic acid. Does that make sense? Okay. Any questions on this example? Yes.
Can we go back to part
Yes,
B?
yes, yes. So let's go through it from the start. So we know that it's a 1-to-1 mole ratio. We know that we start with 5 mils of acid and 10 mils of sodium hydroxide is required to neutralize that acid. So we're going from the volume of NaOH, which is 10 mils, to the moles of NaOH using the molarity. We then go to the moles of acid using our stoichiometric ratio. And finally, we go to the molarity of acid by taking our moles of acid and dividing it by the volume. Does that make sense? The issue is we made a typo and we accidentally put 10 for both of these because one of the previous problems I made had 10 and 10. Yes, this 5 is the volume of acid. The milliliters cancel and we're left with our final molarity of acid of 0.03 mole, just using stoichiometry. Then, in order to compare and calculate the expected volume of NaOH required, we're going to go from moles of acid to moles of NaOH, and then finally to liters of NaOH using our molarity. That in turn gives us a volume of 30 milliliters, or 3.0 times 10 to the negative second liter, which is 3 times the volume required to titrate our monoprotic acid of the same concentration and of the same volume, which makes sense because based on our stoichiometry, it requires 3 times the volume of NaOH, or requires 3 times the moles of NaOH, looking at our chemical equation. Does that make sense? So the stoichiometry is directly tied to the volume of NaOH required. Does that make sense? Yes.
One more question though. How did you get the 10 and 30 milliliters?
The 10 was given in this first problem that it took 10 mils of NaOH. So that's given in part D, right? And the 30 mils was obtained from this calculation down here, or by taking 10 times 3, which is our difference in stoichiometric coefficients. Does that make sense? Mm-hmm. Perfect. Sorry for the typos. This one is the problem version changes, and sometimes I set it up so I'm writing out one problem, then I change one of the volumes at the end, and I forget to change it in all the questions. So let's now do a solution mixture problem. Let's do a mixture problem to finish out this session, or to almost finish out this exam. So we said we have a solution that's made by mixing 130 milliliters of 0.3 molar calcium chloride, 100 milliliters of 0.5 molar aluminum chloride, and 80 milliliters of 0.650 molar magnesium iodide. And we're asked to figure out the molar concentration of chloride ion in the new solution. So first things first, we need to figure out the moles of chloride from each of these solutions. So let's start with calcium chloride. We have 130.0 milliliters of calcium chloride solution. We know that there are 10 to the negative third liter per mil. How many moles of calcium chloride do we have in 1 liter? What's our molarity? What's our molarity of calcium chloride? Yep, 0.300 molar. Okay, and then my question to all of you is how many moles of chloride do we have per mole of calcium chloride? How many chlorides do you see? 2. So then for our moles of chloride from this calcium chloride, we have 0.130 times 0.3 times 2. That in turn gives us 0.078 moles of chloride. Does that make sense? So we're calculating the moles of chloride in our first solution. Let's do the exact same process for our second solution. We have 100 milliliters of our aluminum chloride solution. We have 10 to the negative third liter per mil. We have 0.500 moles of aluminum chloride for every 1 liter. And the key thing that changes is how many moles of chloride do we produce per mole of aluminum chloride? How many chlorines do you see? 3. So that in turn gives us, for our moles of chloride, 0.1 times 0.500 times 3. That gives us 0.15 moles of chloride. Does magnesium iodide, does our third solution contribute any chloride ions? Is there any chloride ion in magnesium iodide? No, so we don't care about it at all. So then our moles of chloride total are equal to 0.15 moles of chloride plus 0.078 moles of chloride. And that in turn gives us 0.22, any questions? 228 moles of chloride. Okay, we next need to figure out our total volume. If we want to calculate molarity, we need the total moles and the total volume. So then, what 3 volumes have we mixed together? What are our 3 volumes? I see 130. What's our next volume? 100. And what's our final volume? 80. So we're just going to add them up. 130.0 milliliters plus 100 milliliters plus 80.0 milliliters gives us 310.0 milliliters, which we're going to convert to liters. They're 10 to the negative third liter per mil, and that gives us a total volume of 0.310 liters. Do we have both pieces of information that we need to calculate molarity? Yes. So the molarity of chloride is equal to 0.228 moles of chloride over 0.310 liters. 0.228 divided by 0.310 gives us a final molarity of 0.735 molar chloride. Does that make sense? Have we seen something similar to this before? Yes, exactly like the quiz. Yes, exactly. And the last problem in our chapter 5 notes. Yes.
So even though we didn't use the magnesium iodide,
You still have to account for its volume. Because it is still contributing to the total volume of the solution.
that's where I messed up. I didn't add it.
Yeah. So even though it's not contributing ions, it is still contributing a volume of water to your solution mixture. So let's take a look at the following equation. We have 35.02 milliliters of 4 molar aluminum nitrate and reacting with 50 grams of potassium carbonate. And we have to balance the equation. And we're asked to calculate the maximum mass of precipitate formed. Okay? So this is a limiting reactant problem. And the way that we approach these sorts of problems is, first and foremost, we need to balance the equation. So I see I have 2 aluminums on the right, so I'm going to put a 2 in front of aluminum nitrate. In terms of carbonates, we have 3 carbonates on the right, so I'm going to put a 3 in front of potassium carbonate. I have 6 nitrates and 6 potassiums, so I'm going to put a 6 in front of potassium nitrate. We know that carbonates are in general insoluble, so this is going to be our precipitate. On the exam, I'll give you the state symbols, as we haven't yet reached predicting solubility quite yet. So if we want to calculate the maximum mass of precipitate formed, what we're going to do is we're going to convert from the moles of aluminum nitrate to the grams of aluminum carbonate. And then we're going to convert at the same time from the moles of potassium carbonate to the grams of aluminum carbonate. And quite simply, whichever compound, when it completely reacts, produces the lowest theoretical amount of aluminum, one moment, produces the lowest theoretical amount of product. Whichever reactant produces the lowest theoretical amount of product is limiting. So then, let's put this into practice. So we're going to go from moles of aluminum nitrate to moles of aluminum carbonate. And we're going to go from moles of potassium carbonate to moles of aluminum carbonate. So now that we have an idea of what we're going to do, let's now execute on this plan in the space provided. So we're going to do a one-line conversion using our stoichiometric ratio. So starting off with, we have 34.02 milliliters of solution. We know that there are 10 to the negative third liter per mil. How many moles of aluminum nitrate do we have per 1 liter? What is the molarity of our aluminum nitrate solution? What are we given for the molarity? Yep, 4.0. Okay, and now my question to you is, how many moles of aluminum carbonate are produced per mole of aluminum nitrate? What is our mole to mole ratio? What is the number in front of aluminum carbonate? What's our coefficient? In front of aluminum carbonate? 1. And what's the coefficient in front of aluminum nitrate? 2. Okay, and then finally, how many grams are present in 1 mole of aluminum carbonate? What is our mole to mole ratio? So let's calculate that really quickly. So we have 27 times 2 plus 12 times 3 plus 16 times 9. That gives us 234 grams per mole of aluminum carbonate. Okay, so now we just have to punch in the single line expression. 35.02 times 1 EE negative 3 times 4.0 divided by 2 times 234. And that in turn gives us an expected mass of 16.39 grams. We are not done. We now need to calculate and perform the same mass to mass conversion for our second reagent, our potassium carbonate. So starting off, we have 50 grams of potassium carbonate. In 1 mole of potassium carbonate, we have how many grams? What's our molar mass in this case? So 39 times 2 plus 12 plus 16 times 3 gives us a molar mass of 138 gram per mole. Now, just like before, how many moles of aluminum carbonate do we make per how many moles of potassium carbonate? What is our mole to mole ratio? What's the coefficient in front of aluminum carbonate? 1. And what's the coefficient in front of potassium carbonate? 3, exactly. Okay, now that we have this established, the mass of aluminum carbonate is the same, 234 grams per 1 mole of aluminum carbonate. Okay, and that in turn gives us 50 divided by 138 divided by 3 times 234 gives us an expected mass of 28.26 grams. So which of these expected masses is smaller? Which reactant is limiting? Yep, the first one, aluminum nitrate. So this produces a smaller mass. So this is the mass of precipitate actually formed. So what this tells us is aluminum nitrate is limiting. So this is known as the product method. You calculate the expected mass of product generated from each of your two reactants, and the smaller mass generated is your limiting reactant. So then we know our limiting reactant is aluminum nitrate. We'll definitely get to limiting reactants before the exam next week. We're next asked to calculate the grams of each reactant that remains after the reaction is complete. Now our limiting reactant, so our aluminum nitrate, the limiting reactant is completely consumed. So we'll have 0 grams remaining. To calculate the grams of potassium carbonate remaining, so to calculate the grams of potassium carbonate, we're going to take our initial grams, which are 50, minus the grams that react, the grams of species that react. Does this equation look familiar from our limiting reactant lab? Yeah. So then, to calculate the grams of limiting reactant that reacts, we're going to take our 16.39 grams of aluminum carbonate. And what we're going to do is we're going to convert the grams of aluminum carbonate into the grams of potassium carbonate. So we know in 1 mole of aluminum carbonate that we have 234 grams. Now the question is, how many moles of potassium carbonate are required to react to make how many moles of aluminum carbonate? Let's look at our mole to mole ratio. So if we're looking at our mole to mole ratio, for every 1 molecule of aluminum carbonate produced, we use up how many molecules of potassium carbonate? What's our coefficient in front of potassium carbonate? 3. So we'll plug in this 3-to-1 ratio, and then finally we know we have 138 grams in 1 mole of potassium carbonate. So in effect, we're going from the grams of product to the grams of excess reactant consumed. And I would look and focus on the calculations in the limiting reactant laboratory for review on this idea. So then, let's punch this into our calculator. 16.39 divided by 234 times 3 times 138 gives us 28.997 grams of potassium carbonate. So our grams of potassium carbonate remaining are equal to 50.0 grams minus 28.997 grams used up. And that in turn gives us, for our grams of potassium carbonate, of 21.00 grams of potassium carbonate remaining. Does that make sense? This is known as the product method of identifying the limiting reactant and calculating the mass of excess reactant left over. Yes?
What was the maximum mass of precipitate?
16.39 grams. So we calculate the expected mass of product from each of our reactants. The reactant that produces the theoretical least amount of product is limiting. And that's the actual mass of product you make. You cannot make more product than your limiting reactant, when consumed, would allow. Any other questions on this example?
So you cannot make more product than the limiting reactant.
Than the product produced when the limiting reactant is used up. Okay, we're now asked to balance some chemical equations. We did a lot of that this past class session. So I'm going to run through these quickly and let's work on these together. So chlorine gas. What's the formula of chlorine gas? Cl2. So we have Cl2 gas. Methane gas, we're given as CH4 gas. They react to yield liquid carbon tetrachloride. What's the formula of carbon tetrachloride? Cl4, yep. And then hydrochloric acid, what's the formula? HCl. Okay, we now have to adjust our coefficients. So looking at this, we have how many hydrogens on the left? 4. So how many do we need on the right? So what coefficient do we put? 4. We have how many total chlorines on the right? 8. 4 plus 4 gives us 8. So in order to match our 8 chlorines on the right, what coefficient in front of Cl2 do we need? 4. Exactly right. Let's look at this next equation. So we have HCl aqueous plus sodium sulfite leads to H2O liquid plus SO2 gas plus NaCl aqueous. Now it's really important that you don't get bogged down too much in these equations. So look, comparing our left and right hand side, what element is found in different amounts in each side? Hydrogen, right? So on the right hand side, we have how many hydrogens? 2. So how many do you need on the left? 2. We now have how many chlorines on the left? 2. So how many chlorines do we need on the right? 2. That's it. It's only just 2 coefficients. Always make sure that your count is accurate and you don't, it doesn't matter all this other stuff that's going on. If it's all balanced, you don't even have to worry about it. Does that make sense? Okay. So let's take a look at another example. Aluminum sulfite aqueous is reacting with sodium hydroxide aqueous to yield aluminum hydroxide solid and sodium sulfite. Okay, now let's look. And when you're dealing with these kind of ionic equations, let's first balance the atoms found in the least number of elements. So notice, is aluminum balanced in this case? No. Is aluminum found in the least number of elements? Is aluminum not found in a ton of different things in these formulas? No. So we have 2 aluminums on the left, so how many do we need on the right? 2. Now, instead of thinking about individual atoms, I want you to think about ions. So how many hydroxide ions do we have on the right? 3? What's 2 times 3? 6. We have 6 hydroxides. And how many sulfates do we have on the right? So, sulfites. Just right here. SO3. How many SO3 units do we have? Just one, because there's only one of them. Okay, so then, if we have 6 hydroxides on the right, how many sodium hydroxides do we need on the left? 6, exactly. And if we have 3 sulfites, if we have 3 sulfites on the left, how many do we need on the right? 3. Does that make sense? So this is a trick for balancing ionic reactions and exchange reactions, is to think about balancing ions instead of balancing atoms individually. Does that make sense? So we balance with respect to hydroxide ion and sulfite ion. This is just a trick I use. You're free to balance based on atoms and you get the same answer. Does that make sense? Any questions so far? Please don't feel shy to stop me on any of these. It's a fast one, right? Yeah. It's better to think about it in terms of ionic chunks. Now let's read through what's the formula of sodium bromide. Let's transcribe this name into formulas. Sodium bromide. NaBr. Yep. And it's a solution, so it's aqueous, and it's treated with chlorine. What's the formula of chlorine? Cl2. What's the state? Gas, yep. It reacts to yield sodium chloride. What's the formula of sodium chloride? NaCl, aqueous, and liquid bromine. What's the formula of bromine? Just Br2. and it's a liquid. Now, how many chlorines do we have on the right-hand side? Oh, on the left we have 2, so how many do we on the right? 2, yeah. So let's put a 2 here. For bromines, we have 2 on the right, so how many do we need on the left? 2. Does that make sense? Okay. This last one seems really complicated, but just really focus on balancing the free atoms last. So then, on the right-hand side, we have how many phosphorus atoms? Oh, actually, let's start from the left. From the left, we have how many phosphoruses? 4. So how many phosphoric acids do we need? 4. That in turn gives us 4 phosphoruses, 12 hydrogens, and 16 oxygens. Okay, let's balance hydrogen first. So to balance out 12 hydrogens, we need how many waters? 6. Okay, so that gives us 12 hydrogens and 6 oxygens. So we still need 10 oxygens. So where do we get the 10 oxygens from? In order to get 10 oxygens, we need how many O2s? 5. Does that make sense to everyone? This is known as the process of serial counting. You balance elements successively and you subtract the elements on the left from your total on the right until you get 0. Does that make sense to everyone? This is another method of balancing equations. So there are a lot of different methods, and I try to show as many as possible in these practice review sessions. Does that make sense? Okay. We're almost done. This is an example of a problem you should be comfortable doing on the exam. This is something you will 100% see. Most of the problems that you've seen on this practice exam will show up in some form on the exam. I'll tamper down a little bit the limiting reactant problems depending on how far we get. This was written assuming we got completely through limiting reactants and even the hard ones. We're likely not going to get all the way, so the problems will be a little bit toned down. If you can do this exam, however, you'd be fine with the actual exam. So the homework would be another good pool of questions to look at for limiting reactants, stoichiometry, and balancing equations. And I encourage you to practice that before the exam on Tuesday. But this is the type of problem that is perfectly fair game that you should be able to do from the information provided, and will definitely finish these concepts and do a lot more practice the class sessions before the exam. So this is completely fair game. So we're given a description of a reaction. Sulfuric acid and ammonia are mixed, yielding a solution of ammonium sulfate. Okay, so what's the formula of sulfuric acid? H2SO4 aqueous. What's the formula of ammonia? That's ammonium, but what's ammonia? Yep, NH3. And they're going to react to yield ammonium sulfate. We've already established the formula of ammonium sulfate. It's NH42SO4. So you're asked to calculate the mass of ammonium sulfate produced when 15 grams of sulfuric acid in 100 mils of water react with 25 grams of ammonia dissolved in 100 mils of water. Does the volume of water matter at all? Is water participating in the reaction at all? No. So what we're going to do is we know we have 15.0 grams of sulfuric acid, and we're going to convert these grams of sulfuric acid to the grams of ammonium sulfate. We're also going to convert our 25.0 grams of ammonia into grams of ammonium sulfate. So we always have to be on the lookout for limiting reactants. So we're going to calculate the expected mass of product from both of these reactants, and then the reactant that produces the least amount of product is the one that is limiting, and it's going to determine how much product we actually get. Does that make sense? Okay. So let's now execute on this idea. So we have 15.0 grams of sulfuric acid, and we know that in 1 mole of sulfuric acid, we've actually calculated the molar mass already in this exam. It's 98 grams per mole. Now, before we report how many moles of ammonium sulfate, how many moles of ammonium sulfate we produce per mole of sulfuric acid, I'm going to need you to answer a very important question. Is this equation balanced? No. How many nitrogens do we have on the right? 2. So how many do we need on the left? 2. Now it's balanced. Always do a mental check when you're doing any calculations involving a chemical reaction. I want you to ask yourself, is it balanced? If the equation's not balanced, you're just wasting your time. Okay, so we know for every 1 mole of ammonium sulfate produced, we have how many moles of sulfuric acid consumed? What's our mole ratio? What are our coefficients? What are our numbers in front? What's our ratio for ammonium sulfate to sulfuric acid? Yep, 1 to 1. So that, and then finally, let's go all the way to grams. How many grams are present in 1 mole of ammonium sulfate? So let's do that really quickly. So we have 14 times 2 plus 8 plus 32 plus 16 times 4. Why does it feel like I've calculated this before? I think we have actually calculated this exact molar mass before. So we have a molar mass of 132 gram per mole. So at the end of this entire calculation, we have 15 over 98 times 1 times 132. We get 20.20 grams of ammonium sulfate predicted. But we're not done. We still need to see how much ammonium sulfate we get from our ammonia. So let's do just that. So we have 25.0 grams of ammonia. In 1 mole of ammonia, we have a total of 17 grams. And my question to all of you, to make 1 mole of ammonium sulfate, we use up how many moles of ammonia? How many moles of ammonia have we used up? 2. Everyone see where the 2 comes from? Okay, perfect. And then the mass of ammonium sulfate is the same, 132 grams per 1 mole of ammonium sulfate. And that in turn gives us 25 divided by 17 divided by 2 times 132. And that in turn gives us a predicted mass of 97.06 grams of ammonium sulfate. So which of these masses is smaller? What mass do we actually produce? What mass are we actually producing? 20 or 97? What's smaller? 20. So we're actually making 20.20 grams of ammonium sulfate. Does that make sense? And that's the exam. The problems will be substantially easier on the actual exam. This practice exam is a little harder than usual, but I wrote it that way because I assumed we were going to get through a little bit more material, but this is a good thing to study off of in terms of the most difficult problems you can see. You'll see another practice exam posted on Canvas closer to the weekend that's a little more tuned once I see how far we get on Thursday. You know, it's a bit of a moving target how far we get in class. So this is the maximum I test up to. You'll likely get problems that are a little easier. You should, at the bare minimum, this last problem you should know how to do, since you'll 100% see something like this on the exam. This is textbook limiting reactants. This is something you should be comfortable doing, as well as the solution mixture problems. Beyond that, you'll get another practice exam later this weekend, and if I have some time this weekend, I'll be able to record a solution, or you'll definitely have the key posted at the bare minimum. Does that make sense to everyone? Yeah, I apologize for some of the typos in this. I usually try to catch them, but since I have like 6 different versions of these exams, sometimes they end up getting crisscrossed. So I apologize again for that. but I hope that this overview was helpful. Any other questions? Yes.
Just on the last one, like how
Yep.
come you chose on 20.20 grams?
The smaller mass of product generated indicates the actual mass of product produced. When the limiting reactant is consumed, that's as far as your reaction can go.
Also, that's why you calculated.
Yes, exactly. We calculate the amount of product generated from each of our reactants. Beyond that, any other questions? Okay. Well then, I will see you in class, and this key has already been posted on Canvas, and this exam is already up on Canvas as well.